great pleasure that I welcome Lloyd, who needs no welcome, to St Andrews as our theologian in residence, who, as he has a habit of doing, is engaging with the knowledge that we have obtained as a human community in the period since the Enlightenment. And this time his focus is on the idea of Genesis and where we have come from and how we understand ourselves and our world in the light of scientific knowledge and as people who are seeking to understand the meaning of life in the context in which we live. So Lloyd, thank you for the work that you do for all of us, and we are delighted to have you speak to us today.
Thank you, Margaret, and good afternoon, everyone. You may wonder why a person who is sometimes referred to as a theologian should be talking about the evolution. Isn't that for the scientists? Particularly the subject today, the emergence of the universe. Well, let me remind you, that's the first chapter of the Bible. So that, in a sense, Christians have always been interested in where it all came from. Indeed, my theological teacher said that theology is Christian experience thinking itself through and relating itself to all other knowledge. Oh, that's a pretty great ask, isn't it? Now, you may be wondering why you should bother about being interested in evolution anyway. After all that's away out in the far distant past or out there in space, and we've got economic problems to worry about. That's what we're concerned with. Well, let me tell you, there's a very good reason why we humans should study evolution. Because the more we understand our common origin of every race and our relationship with the earth, the more likely it is we shall work together to achieve a viable future for all humankind, something that is not at all certain. You see, every culture in the past, every civilization, had its own particular story of origins. But what is the story of the future global civilization, should it ever come? Well, we're all familiar, because of the book of Genesis, with the Christian story. In the beginning, God created the heaven and the earth. And the earth was without form and void, and darkness was upon the face of the deep. And the wind of God moved over the face of the waters, and God said, "Let there be light." And there was light. And God saw that the light was good. And God called the light day, and the darkness he called night. And that was the first day. Well, of course, that story, found in the Bible and the Quran, came from the priests and the prophets of old, who were, of course, the most learned people of their day. And they told us the story of an earth-centered universe created by God in 6 days and about 6,000 years ago. And it told the story that on the 6th day, God created humankind out of the dust of the earth. How did they know that? Language told them. Because the Hebrew word for humankind is Adam. And the Hebrew word for dust is Adama. It's pretty clear that mankind, Adam, came out of Adama. Well, of course, that Christian story has now become obsolete. But we shouldn't laugh at it too quickly. Rather, we should marvel that 2,500 years ago, a group of thinkers wrote that story, and in their context, it was a marvelous breakthrough. So much so that it lasted right up until recent times. But of course, for us, it won't do. We have a new story that has been emerging in the last 200 years, and it is the story of evolution. And this story comes to us from the scientists. Now, the scientists are different from the prophets and priests of old. They always belong to a particular culture. But science is beyond any particular culture. It transcends all ethnic boundaries. Scientists belong to the global culture, and they test one another with the findings that they make. So they today are replacing the priests and the prophets of old. And they are telling the new story on which any future global civilization will be built, if it is built at all. But notice, where did they come from? These scientists came out of the Christian West. There is a real connection between the new story and the old story, though that is something we must look at another time. Now, let's start with one or two of them. In the 16th and 17th centuries, Copernicus and Galileo displaced the Earth from being the center of the universe. No wonder the church at the time regarded them as great enemies, who were in fact upsetting the beliefs that everybody had about where they came from and who they were. And then, in the 17th century, Isaac Newton discovered the force that we now call gravity. That was a tremendous breakthrough. Why? Because it showed that the ways of God were actually the ways of nature. And he, on the foundation of the force of gravity, he was able to forecast what would happen to the movement of the planets. They were not being placed in their position and in their movements by some unseen divine force. They did so by the laws of nature. And so a transformation was taking place in the way we come to understand the world. Then in the 19th century, Charles Lyell and later geologists found out that the Earth was a great deal older than 6,000 years. In fact, it was at least hundreds of thousands of years old, though that was as far as they could go at that particular stage. But nevertheless, they laid the foundations for the thesis of evolution, which Darwin was very shortly to bring in. And they showed that the world came into its present form with its mountains and its valleys and its scenes, not through a series of great catastrophes, but by slow changes, incremental changes over a very long period of time. Now, we may regard the recent earthquake at Christchurch as a catastrophe, but seen on the global scale and over cosmic time, they are simply one of the millions of incremental changes that have been taking place to the surface of this earth. That is what is meant by small incremental changes. Then we come into the 20th century, where the astrophysicists such as James Jeans and Arthur Eddington and Albert Einstein opened our eyes to a universe much vaster than we ever thought it was before this time. Some of you would be like me in the 30s reading these men. I can't remember that I ever read the book The Nature of the Physical World, but I certainly read The Mysterious Universe by Jeans and was quite absorbed by the kind of universe he was opening up to us. Because up until that time, and on the basis of the Bible, we were used to what is commonly called a three-decker universe. Three layers. And we were in the middle layer, the earth. This was, as it were, the world in which humans operated. But above it was a higher layer, the sky, the heavens, the dwelling place of God. And underneath there was the layer where the dead were, the underworld. And when one reads the Bible and the New Testament, one must always try to read it through the eyes of the people who wrote it. This was their world. Take for example, even the great Christian story. The great Christian story was that Jesus, the Son of God, came down from heaven and dwelt among earth as Jesus of Nazareth. Then he died and he went into the underworld. But he rose from the underworld. Forget the story of the empty tomb. What they really meant was he rose from the underworld, the world of the dead. And as he was passing through, he happened to meet Mary of Magdalene. You remember, he said, "Don't touch me, I'm rising. I'm ascending," because he was to go back here to sit at the right hand of God. So that's just one little example of the way in which you must always read the Bible and the New Testament against the background of the universe as they saw it. But that has now been replaced by the astrophysicists of the 19th and 20th century. And it's been replaced, strangely, by another three, but no longer three layers. These are three orders of dimension. And we live in the middle order. I've called it the macro world for reasons you'll quickly see. We could also call it the viewable world. It's the tangible world that we see with our eyes and feel as we touch. But if we multiply it by 1,000,000, we get the mega world. Now that's the world of stars and galaxies, which we're shortly going to describe. While if you divide it by 1,000,000, you get the micro world. It's the world of electrons and atoms and bacteria, which we couldn't possibly see with a naked eye. All we can see is the macro world, sandwiched, as it were, between the mega world beyond in space and the micro world. Now, here we have Einstein in the early 20th century coming up with new theories of relativity which supersede the physics that came from Isaac Newton. The physics that came from Isaac Newton are still true within a limited sphere, such as the earth on which we live. But when you go out into space, you find they no longer are satisfactory, because Newton's laws of relativity operate there. And these laws opened up to us the space-time continuum, which is a four-dimensional universe in which the strangest things seem to be able to happen. For example, nothing travels faster than light, concluded Albert Einstein. But light can be bent. It doesn't travel always in straight lines. And what is more, even space itself is curved. How on earth could that be the case? Well, to try to help you understand that, let me use a balloon as an example of the surface of the balloon as equal to three-dimensional space. And then you will notice that as you move round the balloon, it's curved. You can go a straight line on the balloon and you come back to where you started. Space also is a bit like that. Now that you will recognize as an eclipse of the sun. Well, in 1919, Eddington used the measurements at that point to confirm that Einstein's theory was true. Light bent round the sun from distant stars, and he showed it with his experiment. And then, being a bit of a wit, was Arthur Eddington, he took hold of what was the well-known Omer Khayyam. You'll recognize Omer Khayyam in this, and he wrote a little verse in which he said, "Oh, leave the wise our measures to collate. One thing at least is certain, light has weight. One thing is certain, and the rest debate. Light rays, when near the sun, do not go straight." Now, all this now leaves us with some tremendously big questions. Is this vast universe infinitely old, having no beginning at all? That seems to be a real possibility. Does space extend out forever and ever and ever? Or does it come to a stop? And what sort of stop would it be? But is the universe so immense that we've got to give up even the struggle to think about it? Is it too big for our minds ever to grasp? Well, of course, there's a certain truth in that, and it will always be the case, because we're going to deal today with a universe which is mind-boggling. Well, let's take this space-time continuum that Einstein opened up to us and see some unusual features about it. The universe has no center. No matter where you go in the universe, the rest of the universe will look exactly the same no matter what point you're in. Now, let's go back to the balloon. The surface of the balloon has no center. And no matter where you put your finger on the balloon, the rest of the balloon will look exactly the same no matter where you put your finger. Space is like that. You see, there's no such thing as absolute space, though Isaac Newton thought there was. In other words, if there is nothing, you don't even have space. I once puzzled my father at the age of 14 and said to him, "I'm having a lot of trouble thinking about space." I said to him, "I take out the sun and I take out the moon and I take out the stars and I take us out and I get stuck. I can't think. Thinking of nothing is a tremendously difficult task. There is no such thing as nothing. That's an oddity. Now, space manifests elasticity. In other words, just as a balloon can get larger and larger, and the surface of the balloon expands, so it can with space also, as we shall see. It's elastic. And time and space, the dimensions, as it were, of the space-time continuum are interdependent, so that there is no such thing as absolute time. There is only time relative to us, where we happen to be. But when we move out into space, then we move into the past. So with our telescopes, we can now look back into the past, because what we see is what was there a long time ago. This is someone's attempt to try and simulate the cosmos. It doesn't really tell you anything, but of course it's just a vast mess, really, of bits and pieces. Now, is the cosmos a steady state universe in which the heavenly bodies appear and disappear, and so nothing ever really changes except that they keep appearing and going away again, so that the universe itself is constant? Well, that is what James Jean and Arthur Eddington thought at that stage, that the universe remained the same all the time. So they proposed what they call a steady state theory of the universe, in which matter is being continuously created and also disappearing. And indeed, it was later reaffirmed by Fred Hoyle. You may remember when Fred Hoyle paid us a visit here about 30, 40 years ago. He was an exponent of the steady state theory. But of course, as I say, it was discredited by 1965. Why? Because of what took its place. And this all started with a Belgian priest, Georges Lemaitre, a Belgian who, after his ordination, was sent by his order to go and study cosmology. And he went first of all to Eddington. He was a student of Eddington's for a while at Cambridge. And then he went to Harvard, and that's where he completed his doctorate. Well, in 1927, he proposed a theory of an expanding universe. And he also proposed a theory which later became Hubble's law. In fact, in some respect, he never got the attention and the honor for what he actually did, because in 1927 this was entirely new, and it was only 2 years later that Edwin Hubble, whose name now is attached to this law, provided the evidence which supported an expanding universe with this wonderful new telescope that was then constructed. And what Edward Hubble showed us was that most of the universe is beyond our galaxy. Now, when we look at a star on a starry night at the sky, all the stars we see belong to our galaxy. But what this telescope was able to show was that beyond this galaxy there were other galaxies just like ours. And what is more, when one observed them carefully, one could calculate, because light tends to change its grade of colour depending upon whether it's moving or not. And so what is known as redshift, he was able to conclude that the other galaxies were moving away from our galaxy. That means that the universe and space itself is expanding, and all the galaxies are moving away from one another. Moreover, the further away they are, the faster they are moving. Now that takes a little bit of absorbing and thinking through. When one tries to look outside beyond our galaxy, which after all is big enough, to these other galaxies which are moving away faster and faster. Now here is a typical galaxy. It's actually 60 million light years away, which means that this is what it looked like 60 million years ago. We've gone right back in time, and it looks rather like our galaxy, but it's far beyond it. And then there's another one here, Andromeda. And the stars that you see are the stars of our galaxy. And we're looking through the stars of our galaxy with this tremendously powerful telescope and finding this is another galaxy, Andromeda. Well, if the universe is expanding, can we calculate backwards to a time when it was smaller than what it is now? If it's getting larger and larger, then it must have once been smaller and smaller and smaller. Well, mathematically, it has been possible to do that. And the results of the calculations are these: that the universe emerged 13,720,000,000 years ago. Now, I'm purposely putting this in figures because when you say millions and billions, they sound much the same. And we get a false idea about what a million and a billion is. So we have to see these number of noughts to get a feel for the length of time we're talking about in which the universe has existed. And it began with what they call a singularity. And that's a created term to indicate it was an event which has never happened again. It was a singular event. Now, it is now known as the Big Bang, because that's what Fred Hoyle referred to it rather disparagingly when he first heard of this new theory. Just a Big Bang, he says. And yet, that's the term that is now commonly used for this singularity. Now, why did it happen? There is no reason, no purpose or cause that one can be produced at all for this. Was it by chance? I'd even rule that out. That the universe is here by a sheer accident. And that is when time and space began. You see, there was no time before the singularity, because time began at the singularity, and so did space. And one has to try and imagine energy infinitely hot and condensed to an unbelievable point. That is the singularity. The laws of physics did not yet exist. They had yet to emerge out of that singularity, so that we can say that the singularity was a bundle of infinite possibilities yet to be realized. Well, what was realized, we can now say, are the four laws with the basic forces which physicists have been able to reduce to: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Now, the Big Bang theory depends on some assumptions, two of them in fact, on the universality of physical laws. Why should physical laws be the same everywhere? Well, we can't know. But we assume that the law of gravity, for example, applies everywhere and equally. In other words, the G is a technical symbolic term, is the same everywhere. Well, that assumption comes from the unity of the universe. And the unity of the universe comes actually from a very ancient source. Genesis 1. That's what gave rise to science. That's what gave rise to the idea that everything goes back to one. The Lord our God is one. I'd like to pursue that much further, but I can't do it here. The second assumption was the cosmological principle, which is somewhat similar. The cosmological principle assumes that on a large scale, the universe is homogeneous. That is, no matter where you go, you'll find it's made up of the same basic stuff: energy. Now, to go back to this singularity, I want you to use your imaginations. Try to imagine an infinitely powerful mass of energy, so condensed it takes up virtually no space at all. That was a state of pure potential, infinite possibilities, out of which the universe as we know it eventually came. The laws of nature did not yet exist, only an immense range of possibilities. Compare that with the biblical version, a formless void. They didn't do so badly after all, you know. Now, here's an attempt to look at what's been happening since the singularity, with time coming up and having a slice of the universe cut through it. And you have the singularity there at the beginning, this tremendous explosive force of energy, giving rise eventually to the various galaxies as it keeps expanding onwards. It's simply an attempt to try and help us with our imagination grasp what was going on. Theoretically then, we can go back to a beginning of space-time, a singularity, the Big Bang. Now, in the first few milliseconds, and the astrophysicists by mathematics have been able to work this out by very complex means, I might say. They've worked it right back to the sort of first second afterwards, and have learned how the universe expanded exponentially. It was enormous in a split second. But there was a mystery about this: the speed with which it expanded. If it had been too fast, the stellar dust clouds would never have formed. It would have kept on expanding forever and ever, and there wouldn't be the universe that we know of. But if it had been too slow, the force of gravity would have pulled it all in again to the big crunch, as it were. It's a mystery just why and how the speed was just right. And in this expansion, matter and antimatter emerged. Antimatter is simply the mirror image of matter, except that one has a positive electric charge and the other has a negative electric charge, and when they come together, they disappear. So that matter and antimatter were, in this time, as it were, kept colliding and recreating. It's a kind of cosmic soup of subatomic particles, particles so minute that all we can do is use the scientific names for them. So let's look now at how the cosmos evolved. The universe slowly began to cool from being infinitely hot to being only 1,000,000 degrees, something like that. And the most fundamental elements of matter that came out are known as quarks. But quarks can't exist on their own. Quarks have to link up and become something bigger, and they do so by the nuclear force. Now, the nuclear synthesis, by the process of nuclear synthesis, quarks are gathered together to form into hadrons, baryons and mesons. Don't worry too much about the names. By the way, as I'm saying this, something is happening here about the universe which is going to carry right through the story. The universe has a tremendous innate capacity to join together. Gravity, of course, illustrates that pretty well. It's pulling the bits and pieces together. It also got a capacity to explode, which it had at the beginning. And these two capacities, gathering and exploding, explain a lot of what has gone on in the universe ever since. Now, the most common hadrons are protons and neutrons, terms you may be more familiar with, because they form the nuclei of atoms. Now, the electrons then come to join with the nuclei to form atoms. But it took 400,000 years before this happened. Of course, that's a very short time in the history of the cosmos. But for us, it seems an awfully long time. And in doing so, they formed the simplest atom, which is hydrogen. Now, hydrogen constitutes 75% of the universe. 75%. And the hydrogen gathered slowly into clouds through the force of gravity, clouds which are called nebulae. And in the nebulae, it condensed into stars. And the stars gathered together to form galaxies. And all that is the process of cosmic evolution. Now, a dwarf galaxy, one of the small ones, may have 10 million stars. 1 million is a very big figure. But a giant galaxy may have 100 trillion stars. It's just beyond us to imagine what that really means. Well, that's bad enough. But there are, in fact, 170 billion galaxies in the known universe. 170 million galaxies, and each of them has got this tremendous number of stars in them. But wait. All these galaxies, enormous though they are, may be only 4.6% of the total mass energy of the universe. Why? Because in the latter part of the 20th century, we found that what is predominant is what is called dark energy and dark matter. They're called that because they emit no light. How do we know they're there? Because they've got a mass that affects the rest of the visible universe. And 70% of the universe, therefore, is dark matter. 25 dark energy, 25% dark matter. And dark energy is today's biggest mystery in physics. We have yet to wait for more science to help us understand it. So let's fasten on something we can understand a bit better. That is a star. And look how a star is born. Well, over many eons, a gas cloud composed mainly of hydrogen with a little helium becomes denser and denser and denser until it evolves into a star. And as a star, it has become a nuclear furnace in which the hydrogen now is burnt, as it were, to become helium by nuclear fusion. And our sun is such a star. It's a star of average size. So what happens to stars? Well, a star forms, as I've just said, from a nebula, but they have different destinies. Some become red giants. Some become white dwarfs. Well, some become supernovas. What's the difference? Well, here, first of all, is a gas cloud, a nebula, with no stars, as it were, at all. It's simply dust. But some stars become white dwarfs, which means they get smaller and smaller and then can shine quite brightly, like that one. Or they swell out and become red giants. That is one that is actually visible, Betelgeuse, in the galaxy. It's a super red giant. It's 640 light years away, and it is 10 million years old. A red giant can be analysed as this, with carbon and oxygen in the middle and a lot of helium, and the hydrogen is practically all burnt up. We're told that our sun will become eventually, in about 4 billion years, a red giant, in which case it will have expanded so far that it will have incorporated the planets, such as planet Earth, in the course of it. You don't need to lose any sleep over that. It's a long way away. Now, we're all interested these days in recycling. Well, even stars recycle. So that if we start with a nebula here, in which the hydrogen becomes more and more concentrated until it forms a star, here we have the final star. Then the star may explode. We'll learn more about that in the next lecture, because it becomes a supernova, and part of it hives off as a black hole that I'll mention, while the rest gathers in dust and starts all over again. And so we have, as it were, the recycling of stars. Now, that you can see is a black hole. What is a black hole? Well, it's black because no light can come out of it. The gravity is so strong that it prevents even light from escaping. But it's also called a hole because, strangely, at this point, space and time begin to disappear, as if they're going down the plug hole. And no one knows what is happening to it. Well, at the center of our galaxy, there's a black hole. And this black hole has a tremendous mass equal to 4 million suns. And it, of course, is exerting that gravity in holding, as it were, the whole galaxy together. Finally, one has to mention a quasar. A quasar is the brightest thing you'll ever see in the sky. They don't last awfully long, but they're very bright for a relatively short time. The most luminous object you can see. What is it? It's thought to be a dying star or even a dying galaxy, which is being pulled together into a black hole. And what you see is actually a kind of corona of light around the black hole, which is almost like a despairing cry from a star about to die completely. Or you can think of a quasar as a bonfire of a dying galaxy. Well, some 200,000 quasars are known, but most of them are 3 billion light years away, and you'll need a telescope to see them. Well, this is the story of cosmogenesis. It's been going on for 13,750,000,000 years, and it's still going on, and it's still expanding. We need time to take that in. Time to try and grasp this awe-inspiring reality we call the cosmos. But it was only about 8 billion years before something happened. There, just at that point in time, in cosmogenesis, a supernova, I'll describe them next time, a supernova occurred. And out of that supernova came the Earth and us. And that's the story of geogenesis we'll take up next week. Thank you very much.